Okay. Again, asynchronous machine question. Again, starts with a story, a long, boring one. A given automation motor tracks every second revolution of a slow motor. Okay. It receives a digital signal, RC, from the motor. Whenever a revolution is completed, input RC pulses on for a few seconds and then turns off for minutes until another rotation is complete. Since the rotational speed varies a lot with the load, there could be different amounts of time between input pulses. So that means that we better design an asynchronous machine without the clock, right? Because the load is a variable and we won't know when to turn on the output. The monitor output M turns on when two such pulses are observed and turns off when the second pulse turns off, which means we have an RC signal, okay? We have this RC, which is off for a while, then turns on for a few seconds, and then for some time it's off. And then another pulse comes where we get our output as 1. After the second one, our output becomes 0. Just because this is a variable, this is in favor of asynchronous machine design. Otherwise, if you do it sequentially in a synchronous way with the clock, you have to have additional circuitry that would maybe count the number of off cycles, or maybe regardless of the count of the off cycles, then we would, whenever we observe the second one, we would have the output. Again, you could do it synchronously, but it's better to do it asynchronously since we have some variables on the signals, okay? I mean large variables. Okay, so we are going to design this automation monitor. We are going to make a primitive flow table, and then we are going to convert it to transition table, and then we are going to implement these with SR latches, okay? All right, so let me draw the table. What's our sequence first? We have initial condition 0, and then we arrive, the first one is arrived, and then we have a 0 for some time, and then we have a 1, and then we got a 0. Here we have our output M as 1, and at this point output M will be 0. Okay. So RC is a 1-bit variable, so it's 0, 1, 0, 1. This is for output. This is for next state. This is present state. Okay. Any volunteers to take this one? You should be volunteering to do this on the exam, so maybe you could use some experience on the board. Anyone? Okay, how about I drew it and you help me out on this one? I have a state 1, meaning that I have an initial 0. Okay? My next state is 0. That means I'm still at somewhere here. So my next state is going to be 1, which is a steady state. And if I receive a 1, I get to the next state as 2. And in both ones, in this one, we have an output 0, and I don't know what that's going to be. State 2, meaning that I have a 0 and 1. I receive a 0 next. So I had this one, and I received some 0 next here. So it's going to be state 3. And if I still keep having 1, it's at the same state, so it's going to be a steady state 2, and for which the output is going to be still 0. And for this one, I don't know what that's going to be. So up to here, I have 0, 1, 0 sequence. So if I receive a 0, it's a steady state. If I receive a 1, I have M as 1. I have to go to state 4, and I have 0 as the output, and 4, it's not steady yet, so I'm going to mark with a don't care. State 4, we have 0, 1, 0, 1. As long as I have 1, it's going to be steady here with an output 1. If I receive a 0, looking at my sequence, as you asked in the previous question, it should return to the initial state, which is state 1, right here, with an unknown output. Okay? So let's try to reduce this table, if we can. These ones? We don't know what the output is going to be, because as we move from state 1 to 2, we move here, right? So it's going to be 0 and 0 still. So this better be 0. You can do it as 1, but that would result in your design as a glitch. Yes, we do know at state 2, but for more complex questions, you should follow such steps in order to make sure you won't have any false outputs or glitches in this case. So of course this is going to be 0, and again for 2 is going to be from 2 to 3, again it's going to be 0, from 3 to 4 it's going to be, at some point it's going to be 1. So I would put a 1 here for a more relaxed sum of products, because if I put that 0, I have to take it individually, which would result in more logic. So why not put this one and have an output 1 before it gets to the steady state, and also with a reduced complexity. That wouldn't necessarily be the case, meaning that we would, in some cases, we wouldn't be able to have this reduced complexity plus early output. So you have to make a decision. But I'd recommend you to, for low complexity as your primitive, because in such designs, timing may not be critical, unless the question asks you that we need to output as soon as possible, even a fraction of a second possible. Then I'd recommend you to put a 1 here, so that to have early output. Okay, let's see this one. It's 1 to 4, 4 to 1, it goes back to 1, right? And in this case it transits from 1 to 0. You can either have 1 or 0, right? But if I put 1 here, I have to take this one along with this one, right? So I can either put 1 or 0, but I choose to put a 0, or vice versa. I can put a 0 here and 1 here. But if I put 1s at the both cases, then I have to increase my logic. But in this case, my output would turn off before it gets to the steady state. It won't stay there. Okay, is this clear for you? Okay, good. This is an interesting point. Thanks for the question. And okay, so anything to reduce here? All have individual meanings. We have 1, maybe 1 here, but 2, 4 doesn't count. We don't have any don't care, so it's really hard to reduce it. It's not reducible. So this is also the flow table itself. Okay. Let's put this to, let's transfer it to transition table. We are going to have S or in this case A, B. We are going to have A plus B plus as 0, 0 and as RC 0 or 1 and output as 0 or 1 depending on RC. We have, okay, before we move forward with the state assignments, let's decide on which states that these four numbers gonna get. So we have transitions from 1 to 2, and then 2 goes to 3 only, then 3 goes to 4 only, and 4 wraps around to 1. That's it. Okay, and if I start with 0, 0, I better put this 0, 1 or 1, 0, doesn't really matter. For 3 it's going to be 1, 1 and 4, 1, 0. Quite simple, quite straightforward. We won't need any additional states to avoid hazards. So I'll just map these using that information to here as 0, 0, 0, 1, 1, 1, 1, 0. Again, this eases your K-map transformation, okay? This order. So it's 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0. And my outputs are 0, 0. Let's put these 1. Okay. All right. Now the final question is how to do this with SR latches. If you remember from your digital design course, we had an SR excitation table which may be given to you during your exam or not. So, but it's quite easy. Set and reset, right? Let's make it this way. I'm going to decide on S and R variables depending on the present and next states. Okay, so I have Q and Q plus, and I have S and R. Okay, 0. So what I'm going to describe here is a bit tricky, but it's not that difficult. I had my Q as 0 previously, and on the next state I had my Q as 0 again. So this can be done with reset or retain state, right? It can retain as it is, or it can be reset, right? So we know that S is going to be 0, and reset can either can be 1 or 0. So it's a don't care. Okay. This, my initial state was 0, then I had a 1. What is this? This is definitely a set. So it's 1, 0. I had 1, the next thing I know it's 0. This is definitely a reset. I had 1, and then I had 1 again. This is either retain state or a set. So in this case I have reset as 0 and set as X. Okay. Using this information and this table, I'm going to implement the SR-based K-map. So for each input, I'm going to have 2 K-maps, right? One for S, SA plus, RA plus, and then SB plus and RB plus, which all of which have three variables, the RC and the present states. Okay. If you notice this structure at this table, it goes like 0, 0, 0, 1, 1, 1, 1, 0. And the other one is 0 and 1. So I'm going to implement a map for you that is for SA plus and then RA plus. And I'm going to put my RC right here as 0 and 1 exactly as it is there, and A, B in the same order. So RC, A, B. Okay? And then I can directly take that information and map it here. For A, how do I do that? Using this SR. So for the first one, we had an A as 0, and the next thing with RC 0, it's 0, right? Whenever it's 0, 0, we had an SR as 0 and X. So we don't map those zeros, but using those information, we map whatever it corresponds to in the SR latch, okay? This is important. So I'm going to, for S, I'm going to put a 0, and for R, I'm going to put an X. So it's 0 and X. Okay. How about the next one? Any volunteers? We had a 0 for A, which goes to 1 in one case, and which goes to 0 in the other case. Or let's continue with the first one. We had a 0. Again, it becomes 0. So again, it's a 0x. How about the second one? So we had an A as 0. The next thing we know, it's 1. 0, 1 corresponds to 1, 0. Okay? And how about the rest? We had an A as 0, and it's still 0, it's 0x. The third row, we have 1. The next state is, in one case it's 1, other case it's 1 again. For 1 ones, we had x zeros, right? X 0, x 0. Finally, we had 1 to 0 and 1 to 1. 1 to 0 is 0, 1. 1 to 1 is x 0. 0, 1, x 0. So I can take this like that, right? I can't go any fancier. For this one, I'm limited to here. So my SA plus is going to be, it's B, right? With RC bar. B, RC bar. And RA is going to be it's B bar and RC bar. You can do likewise for SB and RB, and that's it. Any questions so far? All fine? Good. Mustafa? Okay. I hope you'll do great in your exam. This is the end of the computer architecture recitations. So We'll be seeing you next semester.